Hello everyone, I'm Vineet. Today I'm going to present the discretization algorithm to find a semi-optimal set of cuts. This is the algorithm which we have implemented in our project. So to demonstrate the project and the algorithm, we have used the decision table as an example here. So in this example, we can see we have the column A and column B having continuous values. So these are the two columns which we'll be discretizing in this example, and D represents the decision attribute. So the first step of this algorithm is to basically list out all the domain values within the column, and then sort it out in an ascending order. So as we can see in example A, we have 0.8, 1, 1.3, 1.4 and 1.6. Similarly in B, we have 0.5, 1, 2 and 3. So after sorting it in ascending order, we will basically generate the possible cuts between the values. So as we can see, one cut would be from 0.8 to 1, 1 to 1.3, 1.3 to 1.4 and 1.4 to 1.6. Similarly for column B, we will have a cut from 0.5 to 1, 1 to 2 and 2 to 3. So now what we will do is we will take each and every row and then we will compare with all the other rows. So here we will basically only compare the rows which have the where the decision attribute is not same. So as we have here, right? So let's take an example of row 1 and row 2. So x1 and x2. So here as we see, if we compare this both, we see that the decision attribute is not similar for the both of them. So we will continue the comparison, and in order to write it this way, we'll basically uh, check the range from 0.8 to 0.1. So over here we can see 0.8 to 1 is p1, so we will write p1, and then for the B we have 0.5 to 2. So 0.5 to 2 comes in q1 and q2, so we'll add q1 and q2. So now as we move from x1 and x2, x1 and x3, we see that the domain has 1 for both of them, so we will have to skip that one and we will move to x1 and x4. So we'll compare the domain. So okay, so domain is 1 and 0, so we can continue with this x1 and x4. So here we see the range is 0.8 to 1, which is p1, and we see the range for B is 1 to 2, so that is q2. So similarly we will compare each and every row with the other rows, and we will get the uh, uh, all the formulas like this. So now once we get the formulas, we will basically create the table. So this is the table B. How this is generated is basically we write out uh, all the ranges. So it's P1, P2, P3, P4 for the A, and then Q1 and Q1, Q2 and Q3 for the B. And then so let's say in the x1 and x2 we basically found p1, q1 and q2. So whichever values we have here, we'll add 1 for each and every uh, for each and every column, and similarly we will create the whole table. So now the next step is basically is to check whether to check which column has the highest amount of ones, and we will take that, and we will remove that column and all the columns which contains ones. So here in this example, all this column, all these rows will be also deleted along with this column. So after removing all the rows and columns, we end up with this table, and now we will further continue until and unless we have an empty data set, right? So here we see the column count for q2 is the highest, which is 2. So we will remove this column and all the rows which contains 1. So now we end up with only q3 and p4. So we take the Q3 since it is the only column left now, and then we basically remove that. So now we end up with columns P2, Q2 and Q3. So here are the cuts for the P2, Q2 and Q3. So in order to create the optimal cuts, we basically take the range. So we take the average of 1 and 1.3, which is 1.1. So in our optimal cut, it would be from 0.8 to 1.1 and then 1.1 to 1.6. And for B, it would be we take the average of 1 and 2, which is 1.5. So it would be 0.5 to 1.5, and then again 1.5 to we take the average of 2.2 and 3, which is 2.5. So it would be 1.5 to 2.5 and then 2.5 to 3. So after getting the optimal cuts, we basically replace the values for A and B according to the new optimal cuts which we get. So this is how we basically optimize, how we basically discretize the column A and B. Thank you.